Hello, everyone.
Hello. Hello.
Hello, ASU Prep Digital students. Welcome. I'm Mrs. Bilkin for those of you who are coming in from other classes, from our chemistry and physics classes. You will be off camera and off mic for our visit today, but please utilize the chat box and the question and answer box to ask questions as we go throughout our interactive journey. Just remember to keep high professionalism and school standards. You are representing ASU Prep Digital, but we're excited to have you and to continue with this virtual visit to the CMS. So I'll hand it over to our guides to introduce themselves.
Great. Hi, everyone. My name is Claire, and I'm a South African working here at CMS for a Hungarian institute.
Hi, my name is Andres. I'm originally from Puerto Rico, and I've been based here at CERN, working for CMS for quite a few years.
Hi, I'm Collin. I'm a graduate student at Rice University in Houston, Texas, but I'm originally from Michigan, and I've been based here for the last couple of years.
So we are going to take you on a virtual tour of the CMS detector today. Right now, where we are, we can show an overview picture of the region. We are all the way over there on the left-hand side that says CMS. That's our amazing, beautiful detector. And the CMS experiment is one of 4 huge experiments at the Large Hadron Collider.
I'm actually gonna get going. I'm just gonna get ready to head downstairs, but you guys take over.
Oh, yeah. Sure. Yay, so we can tell you more. So the Large Hadron Collider is a particle accelerator. It's the world's biggest particle accelerator, 100 meters underground. How many feet is that's about like 300 feet underground in the Geneva region. And the tunnel for the Large Hadron Collider is almost 17 miles long. And in it, it takes protons, like right the center of an atom. What we do is we actually start off with a hydrogen atom.
Yep, we start with hydrogen gas, and then we heat it up and remove all the electrons. And what we're left behind with are just pure protons. And then we inject those into the collider and accelerate them to super high energies, and then we direct them into each other and at these 4 different experiments. CMS being one of the 2 main purpose detectors. CMS and Atlas, the 2 that discovered the Higgs boson you might have heard of.
Yeah, so let us know if you heard of the Higgs boson before. Do we like science? A little bit, just a little bit. It's a little bit fun. What not to like about smashing things together and seeing what happens. Yeah, so we both work on different parts of the CMS detector. So actually I got this. We've got like a little 3-dimensional little 3D printed version of our detector. In reality,
colorful in life.
No, unfortunately, it's not rainbow colored in real life, which would have been fun, but they had to make it a little bit more practical than that. In reality, though, this thing is 15 meters from top to bottom and 28 meters in length. So it's really, really big. There's a picture on the screen coming up soon with all the different layers. And the way that we built this thing is kind of like a big cylindrical onion or cake, because they both have layers. And each layer measures something different about the particles.
Right, yeah.
Like here.
Yes. So these are super tiny things. We can't see them, right? So we have to in order to make measurements, we have to look for things we can see. So sometimes that's just the path the particle takes. Sometimes that's how much energy is deposited. So this onion kind of like layered detectors, each one measures a different thing, but we can put all that information together to try and describe these tiny particles.
Like an ogre, exactly. It has layers like an ogre in it.
Yeah, but not as stinky.
Oh, sometimes the physicists get a bit.
Yeah.
No, I'm just kidding. Andres, what are you up to right now?
Andres, some picture.
So,
yes. Okay, yeah, we just unmuted. Right, so we're just going through the personnel access device. And so I just went through, and Noemi is now going through this box this booth that you see here. And yes, we have to scan our dosimeter, and then we have to maneuver ourselves into this booth, and then the system will take a photo of our iris and then compare that to the database. And it's just one of the ways to make sure that the person who's, who's at the downstairs, the underground areas, actually has all of the rights associated with them, and it's actually the person who is who the dosimeter belongs to. Okay, so we're gonna head 87 meters underground, but our detector, as we already said, is about 100 meters underground. We're just calling the elevator. And yeah, one of the things that we can also show is this blinking light that's showing us that there's a magnetic field that is currently on. And in fact, we are ramping up the magnet. So we had a interruption, let's say, there were some activities that required the CMS magnet to be turned off, and it's now being turned on. I'll let my colleagues explain a little bit about that. We're just going to get in the elevator and yeah, we'll just meet you guys downstairs.
Sure, thanks, Andre. See you down there. Yeah, so we're talking about all these layers of CMS, and the different layers measure different types of properties of the particles. So when we put all of that information together, we could tell the difference between an electron or a proton or something like that. And we have a big magnet. So this magnet, the solenoid magnet, is how many tons? I don't know. Normally it sits at 3.8 Tesla magnetic field.
Which is 100,000 times Earth's magnetic field.
That's huge.
Very
Which is
strong.
very strong.
That is very strong.
But indeed, it is not. Oh, sorry, my monitor. It is somewhere in the range of the MRI machines in every county hospital.
Yeah. So you're not allowed underground if you have a pacemaker or anything like that, because it can, mess with your magnetic field. But the nice thing about having this magnet is, as I'm sure you know, magnetic fields bend charged particles. And so positively charged particles will bend in one direction, whereas negatively charged particles will bend in a different direction. And that's one of the ways that we can tell the difference between the different types of particles. How are the cameras working down there without hindrance from the magnetic field? They've got very special cameras. In fact, outside where they're going now underground, it's not so bad, but when you go right into the actual experimental cavern, which unfortunately we can't do today, but if you go right next to the detector, then they have to change the stand that the camera's on, because the gimbal doesn't work so much.
Right, and the number we quote to is for the middle of the detector, 3.8 Tesla, but the further you get away from it, it falls off like 1/r², right? So it becomes much weaker, and they're standing pretty far. I mean, once you get even to the outside part of the detector, it's already down to 2 Tesla.
We measured the value where they will visit, and that's something like 10 millitesla. So
Okay.
that decays from the 3.8 Tesla to 10 millitesla. Well, after the iron yoke and the 7-meter concrete or iron and concrete pillar.
The ghost voice you're hearing, by the way, is Zoltan on our technical team. He doesn't like to be on the camera,
Yeah.
but
Well,
like this.
I just don't fit.
Yeah. So Andres is showing us a lot of electrical cables. What is going on there, Andres?
Yes, so we are in what we call the service cavern, and what you can see around me are all of these electronic components. So very briefly, what you see around me are a lot of power supplies and a lot of readout systems, and most of the readout that we have for our detector is using fiber optics. So most of the cables that you see here, these are all fiber optic cables, and you can see the amount of electronics here. So part of what's interesting is that this is all, custom designed, and it had to be developed by different institutes. So something I'm gonna try to show you guys as we go along is there's every now and then you can find some stickers from a university or something like that, and yeah, you can see there's a lot of fiber optics. Some of these systems are what we call the data acquisition systems. So we do have to take a lot of data from different subsystems. So different kinds of data that gets sort of funneled together. Then there's a sort of, a process, right? So we have what we call the trigger that has to filter some of these data. So I'm not going to go into detail. I'll let my colleagues talk a little bit about that. But we'll go around and show you some pictures of the underground area. And if you guys see something interesting, feel free to ask. If there's something that you would like me to show, let me know. But we'll just kind of walk around and show you what's down here.
Just to give you a bit of context to where Andres is, so we have our detector underground with the, along the ring. So the LHC ring is around it. But when the LHC is running and protons are colliding, this produces a lot of radiation. So you cannot have people in the cavern there. It's too dangerous.
Go
However, Gators. However, we do need to be able to access like a lot of the things and stuff that doesn't need to be right there in the same cavern. We've built another cavern right just next door, which we call the service cavern. And that's where Andres is walking around now. We can't go into the cavern with the actual detector because the LHC is about to inject a whole new batch of protons and accelerate them again. But we can walk around underground and see all of the other really cool stuff that's there. So there was a really nice question asking what specifically does CMS detect compared to the other experiments running at CERN. So as we mentioned, there are 4 experiments at CERN. Atlas and CMS are general purpose detectors. And that basically means they're designed to catch anything and everything that comes out of the collision point. Whereas ALICE and LHCb are highly specialized detectors. So ALICE is specifically designed to look at what happens when we collide not protons, but lead ions. And when that happens, we create something called the quark gluon plasma, which is like this goopy superfluid state that the universe was like, right at the beginning of its life. So the ALICE detector is specifically designed to look at those type of events. And LHCb is another very, very high precision. In fact, it's the highest precision of all the detectors. And it's designed to detect or to pick up differences between matter and antimatter. So you create very special types of particles. It doesn't care about all of the other types of things they create. But when you get a very, very particular type of particle, it looks at whether it decays to matter or antimatter.
Yeah, just after one of the most intriguing question of the universe, a fun fact. These names are acronyms. Sorry.
They're terrible acronyms. Yeah, but they are acronyms.
Well,
See,
except the LHCb. That's not an acronym.
it's a
the
LHC is an acronym.
Beauty. Well,
Like
the
it
LHC
is, it's all an acronym. They're all
but the
acronyms.
L everywhere is it refers to the LHC, and the L is Atlas.
Toroidal LHC.
A
Correct.
toroidal
Apparatus.
LHC apparatus, or a large ion collider experiment.
And CMS is compact muon solenoid.
Well, since it is small.
Yeah. So maybe one of you guys can, build an experiment and give it a better name. We're hopefully going to build more bigger ones in the future. So you can start thinking of cool names for your detectors now.
That's it's part of the job.
Yeah. Very important
So,
part of the job is naming.
Guys,
stuff.
is this, sorry to interrupt. I wanted to show a couple of things since we're down here. So this is as close to as we can get to our detector right now. And as Claire was saying, we're now in what we call the service cavern. So yeah, this wall that is just in front of me is actually, it goes down the length of this space that we're in, and it's 7 meters thick, right? This is like 20 feet wide, and it separates us from our detector. So if we were to access our detector right now, we can't, because you can see like everything is closed. The access device is all closed. But we would go through this door, and then we would go in, and then we have to walk 20 feet to the left to basically go around this wall.
Currently, I'm just showing it on the map.
Yeah, so this is what you can see in the figure from above. It's what's referred to as the pilier. And I wanted to show you, we mentioned the magnetic field is now ramping up, and we talked a little bit about the effect of the magnetic field. So when it's fully ramped up, it's a lot more obvious, even in this area. For now, the only trick that I can show, The only trick that I can show you is
Cool.
gravity, obviously. No. So if we get closer, this is more obvious. So you can, if I get closer, you can see,
I guess we're about half
right,
now.
that this paper clip is pointing in the same direction. And it's acting like a compass, right? So it's pointing in the direction of the magnetic field. So that's something that is just about the only trick that I can show you. There's normally we would have these things stick. Yeah, this one
We are
sticks
currently
already.
at 1.8 Tesla.
Okay.
Yeah, so yeah,
Good.
we're 1.8, so more
Not
or
quite
less at half
halfway.
the magnetic field. Okay, so we're gonna continue to go around and show you guys a few things. So we're gonna also show you the infrastructure just under the racks that we have here.
Andres,
But yeah, I'll yes.
Before you run away, what is that like triangular sign above your head over there? Yeah, that one.
Clochard.
Yeah, so
Yeah.
this is the sleepy guy, right? So
Yeah.
this is the alarm that when you're down here and you haven't had your coffee, this helpful alarm will, start making noises so you can wake up. Of course, none of
Exactly.
that is true. So this alarm is actually what we call a oxygen deficiency hazard alarm, and so this will fire when the oxygen level is below a threshold, which I made 15%, it's something like that, maybe a bit lower. I don't remember exactly. But in any case, the thing is that we work with a lot of gases that can displace the oxygen from the air. So there's a lot of gases that might be inert, but if there's a leak of any of these gases, then it means there's just less oxygen in the air. So depending on the situation, we will generally just evacuate, but we're also trained to wear these self-rescue masks. We can show you what they look like. So this is one of the trainings that we have to do to be able to access these underground areas. And you can see it's a very interesting device. It's not really an oxygen mask at all. It's actually a device that converts the air that you breathe out. So it's taking CO2 and it's actually converting that into oxygen that then you can breathe. So, and since you mentioned some chemistry at the beginning, so this happens to be an exothermic reaction. So while you're wearing this device, you're breathing out and the oxygen that you breathe in is actually warm because of this exothermic reaction. So it might be a bit unpleasant, but it will save your life.
I think on the back as well, there's actually like a little pad so that
Exactly,
your tummy doesn't get burned.
Yeah, thermal isolation. Actually, what came to my mind that this is, as far as I know, this is exactly the same chemical reaction that the astronauts use on the International Space Station or on the Artemis. Yep. No, they have to recirculate, refresh the air somehow.
Yeah.
Otherwise, the mission would be very short.
I was rewatching Apollo 13, which is, with Tom Hanks, which is like one of my favorite movies ever.
Yeah, that
where they had to
something
rebuild
similar.
the scrubber and put the square thing in the round hole, or vice versa.
Yeah, the best bricolage of the human history, I guess.
Speaking of Artemis, did you know that some detectors, so at CERN, we build particle detectors to, in our experiments, but then people have also found ways to take them and, create them into stuff that's useful for, daily life. So there's a little detector called the Medipix detector, which we can do things like colored X-rays and stuff. It's very, very cool. But there was a bunch of these that actually went on Artemis around the moon, and they were measuring the radiation dose inside the capsule.
And indeed, your home institute created a radiation measurement unit back in the 80s that is still operating on the ISS.
That's so
This
cool.
is the pillar. That's a very important thing of that institute.
You see, so we don't just do stuff 100 meters underground here.
Right,
We
yeah.
do. All right. So anyway, there's lots more cables. There's a lot of cabling around. If you like,
What is that? Is high voltage? That's high
Oh,
voltage.
he's under the floor.
He's under the floor, and he's currently close to the RPC high voltage cables, 10 kilovolt in each.
That's
So
awesome.
be very careful.
Plus a random lonely chair.
Yeah, actually, we can go back to the surface in just a second and show you what they look like, because each of these very thick cables actually contains multiple cables inside of them. And as Sultan said, it's you know, quite a few kilovolts each.
Current is very
Careful,
small.
Andres.
Current is very small, but if you short it down, you will feel.
There's a reason why we have a defibrillator down there.
There's actually something else I can show you guys. So let's show you the RPC. So this is one of the muon systems. There's many acronyms. So RPC stands for resistive plate chambers. And you can see what these red cables look like when they're actually plugged into high voltage modules. And yeah, as you can hopefully appreciate, it's a lot of cables and it requires a lot of organization to make this work. And yeah, and just as on that note, right? So we're going to talk a little bit more about the upgrade a bit. So we are in 2026 going to be producing collisions until the end of June. And then after that, everybody's going to go on holiday for a couple of years. And, you know, we come back in 2030, all, you know, fresh, ready to go. Of course, not at all. So we are hard at work, and we've been hard at work for several years now to prepare for this really dramatic updates that are coming up. And the whole idea is we're going to radically increase the rate of collisions that are happening at the LHC. So we call this a high luminosity LHC. And I can show you one of the things that's going on in anticipation for that. And I will try to hurry up so we have time and show you on the surface what the status of the project, you know, what you can really see already. But what, you know, to give you an idea of what it entails, we have to redo all of the cooling systems that actually keep these new detectors will keep them very cold. So all of this infrastructure is brand new, and this is dedicated to a type of cooling system that is using CO2. So it's a two-phase CO2 cooling system, and this will provide or maintain these detectors at temperatures of something like, I don't know in Fahrenheit, but it's like minus 30 degrees centigrade or something like that. And it's
Close,
a lot of
minus 40 is minus 40.
Yeah.
Yeah, so okay, pretty close. But yeah, all of this infrastructure is, you know, being put together right now, and it's been several years. In fact, some of the manifolds that go into our detector, those were installed years ago in like, you know, 2020 or something like that. So a lot of preparation that's been going on for several years. I think we will show you a few more things underground, but then we will start heading to the surface soon. If there's anything you guys want us to show, let me know.
So there's a nice question about like how many people work on maintaining all of these connections and cables and everything. So let's just say the CMS experiment has what, 6,000 people
6,000
roughly?
people,
Yeah, something like that.
Yeah, but most of them never come here.
Yeah. So that is everybody from the people who literally spend every day going underground and making sure that the racks are okay, the connections and
200.
things.
Yeah.
Yeah, a couple hundred there. Then general people who work here, like all the shifters here in the control room and the people managing the data flow, plus the physicists around the world, loads of PhD students as well. And yeah, each depending on which part of the detector. So for example, you work on CSC, right? Which are these outer guys.
Yes.
I work on the tracker, which is like this really
You are not fully on the picture. Let me just put you on.
Yeah, so CSC is another acronym that stands for cathode strip chambers. We'll have a quiz at the end with all, you know, for all the acronyms.
Whereas I work on the tracker, which is the silicon detector right in the center. And so we each have like our own team of people dedicated to doing various bits of this.
Yeah, every single subdetector system has a whole team of hundreds of people working on it. As you get closer and closer to the actual hardware, then you have fewer people actually touching it, because you don't want hundreds of your colleagues like, you know, oh, I think it should be wired this way, I think it should be wired. So hundreds of people all around the world.
Maybe I could, I don't know if I can interrupt, but I quickly wanted to show we're in the elevator shaft right now. And you can see about, what is this, like 70 meters up, something like that?
Yeah.
70, 80 meters.
Yeah. Yeah.
But something I wanted to show is on the left, you see these bars that go up. And these are what we call the bus bars. These are part of the magnet system. So this is what carries the current for the magnet. And they have to be extremely robust because we're talking about 18,000 amperes of current when the magnet is fully ramped, right? So we have to inject all that current. And in some scenarios, we have to remove the current rather quickly. And so that means that these bars have to always have water circulating inside of them. Otherwise, they would melt. So there needs to be constantly water circulation inside of these bus bars. And yeah, that's like one of many layers of safety systems. Just something I wanted to show. And then we're going to go into a room
Andres, I have a number before you continue on this. We have, as it is a superconductive magnet, we store the energy inside the magnet. And this energy is somewhere around 2.2 gigajoule, which is close to a kinetic energy of a wide body aircraft.
That's amazing.
Yeah.
Indeed, we all seen those sad images when they are crash landing. We don't want to have it here, 100 meters below, and that's why we have this bus bar. Its main purpose is to pump out, as Andres said, pump out the energy of the magnet in case we need. We have a resistor network on the surface to dissipate this energy, and as Andres said, this is a water-cooled system. This is always maintained.
Where does the water come from?
This is the main cooling.
It's normal.
Yeah.
And it's recycled, or?
This is the same cooling system that we use.
So just to
indeed
add,
that.
not to interrupt, but just to add that, as Zoltan said, it's a lot of energy, but in fact, this is the most amount of energy stored by any magnet on Earth right now. This is a record that we hold right now in CMS. We've held for a few decades. As soon as ITER is in operation, they will take that record. There's many records that ITER will take once it's running. But right now, our magnet in CMS is the magnet that stores the most amount of energy of any magnet in the world. So very quickly, I wanted to show you guys.
Hold on, before we do that, people were asking about the lights going up the shop. Those are pure just LEDs put there for fun.
That's an artistic. That's an artistic thing of
not showing
demonstrating
anything more
how
than
the data comes out from the experiment.
Yeah,
but nothing to do with the timing of the spacing of the bunches. There are some urban legends on the distance between the two light bunches. People find some coincidence with this between this and the distance of the two bunches in the accelerator. That is something like 7.5 meters. I happen to know the guy who made it, and the guy said that it is just a technical coincidence. It was limited by the equipment's technical capability. But
so what Zoltan is talking about, and this actually answers somebody else, I think like a different another question here is, okay, let's do a couple of them all at once. We're gonna just, if we have the LHC, right? The LHC is a ring. It's got two beam pipes. So one has protons going in this direction, one has protons going in the other direction. Now, what the LHC does is it takes protons and it fills up the tunnel full of lots and lots and lots of little bunches of protons. And these bunches of protons are spaced 25 nanoseconds apart. So you have a whole bunch, something like
you have about 3,000, like 2,800 going in either direction.
Going in this direction, like 2,800 bunches spaced 25 nanoseconds apart, all like going at light speed in this direction, and then you have another 2,800
going
spaced 25 nanoseconds apart going at light speed in this direction.
And each bunch has about 100 billion protons in it. And then when we point them at each other, and so we get two bunches right in the same space, we get about 200 billion protons, like right at the center of our experiment, but only about 60 of them collide. It was designed for something like 20, 25, but we've pushed it to about 60 now. So
out of 100 billion, every time they cross, we get
60
60.
collisions.
Indeed, we got a picture here.
Yes,
And
that's,
this picture is a
that's a 25.
it's a zoomed in picture of the interaction point, indeed. And what you see, what happens when the twice of 100 billion protons bunch cross each other, every yellow dot means a proton-proton collision. It's something like 60, 70, it depends on how many protons we have in the bunch. But you might imagine that this is a very finite number of yellow dots with respect to the 200 billion.
Right. So all that to say, the beam is not completely wasted when we run into each other. We keep circulating it. And because of that, we can, someone asked, the collisions are happening at the same time in all 4 experiments.
Yeah.
So yeah, because 60 collisions of 200 billion, we can run for about 12 hours before we have to empty the beam and then refill and start over.
And every bunch in the ring goes through the center of each detector.
Yeah.
But not every bunch collides in the center of each detector. So the LHC is actually kind of clever like that. The reason why Atlas and CMS are exactly opposite is so that they can make the same bunches collide in our detectors. And then the other 2 detectors are slightly offset, so they can make different bunches of protons collide in those ones in different amounts.
What you might see on the picture, this is how the bunches collide. So each blue and red blob represents this 100 billion protons package. They are redirected to each other with a very shallow angle. Actually, this is very much exaggerated in order to see what happens, but they are colliding at a very shallow angle, practically minimizing the vertical momentum of the system. We want to have 0, but technically it is impossible to make 0.
Yeah.
But it is very close to that. Indeed, every bunches have a radius of something like 100 micron, something like, and they collide practically head-on with each other. It is a very complicated thing. Indeed, not very hard. It is something like shooting through a needle of an eye of a needle, if the needle is on the moon.
Well, it's so complicated that beam physics, the type of people who work on the physics running the accelerator, is a completely different part of physics to the type of physics that we do, which is just analyzing like what comes out of those collisions. And so there was a question. So these protons are going at very close to the speed of light, 99.9999991.
7 nines.
Yeah. And so to go the 17 miles, how long does that
it takes? One proton will go around the full ring, so almost 17 miles, 11,000 times a second.
Yep.
So it is super fast.
11,000 times per second. So that it's
it takes
17,
us half an hour to
17,
get here
not
from
70.
now.
But yeah. So that's how fast the protons go. And how often do the collisions happen? Well, we said every 25 nanoseconds. And when the LHC is running, it'll run for, they try to do it as 24/7 as possible.
Right.
So 40 million times per second.
Mm-hmm.
Now, to go back right to the beginning of this segue about the lights and the spacing. So because we have protons going at light speed, 25 nanoseconds apart, you guys can do the math. But 25 nanoseconds going at light speed is roughly 7.5 meters.
I wanted to say, don't tell them the result.
Left this as a homework question for you. Well, yeah. So that's why they were laughing about, in the light spacing was about 7.5 meters, and it just kind of worked out right. So it looked like.
I love the urban legends.
I think Andres is dying to show us something. Oh no, he's in the
no, he's inside the elevator on the way up, but he's not going to be disconnected on the way up.
Okay.
Yeah.
That's the peculiarity of the radio communication between France and Switzerland. Oh, okay,
that's also pretty interesting. But yeah, we're gonna go up to the surface and show you a few things as well.
Cool. In the meantime, since you're leaving the radiation area, Andres, can we Can you tell us a little bit more about your dosimeter and what the personal limits and stuff are? There's a question here about, what our personal limits in that are.
So, yes,
you don't have to give
you've
numbers,
put me
but-
on this. Yeah, I
Sorry.
don't actually remember. All I can tell you is there are legal limits in France and Switzerland, and CERN adopts the most strict of these limits. But one thing I can tell you is we always, in order to have access, these kind of underground access, we keep this personal dosimeter with us. And when we actually go into the detector, we will have an additional dosimeter that we call the operational dosimeter. And so that will measure the dose that we get during that session. So it's a more detailed measurement of the dose that you're getting.
Yeah, there are limits, and there's limits. So there's a limit on how much you're allowed to get in a short period of time. And then also a limit of, even if you get like a small amount, how much you're allowed to get it adding up to over a full year.
So indeed, of course, we have a limit for the dose rate, as we call.
Yeah.
But indeed,
should we go this way?
the integrated dose that we are subject to get during a year.
Somebody was asking
3
about the.
millisievert. This is exactly the same as the general public. We are not exceptional to that. We are not glowing in the dark during the night. Absolutely fine. And I will ask Andres at some point to read out his dosimeter. I know that this is probably against the privacy rules, but if you agree,
It's absolutely fine. So this is my
Colin's
dosimeter, and you can see the station here. So I'm gonna insert my dosimeter, and you'll see that it's connecting to the database, and you will shortly get the results. Let's see what we have. Drum roll. Oh no, I have an overflow. Well, that's unexpected.
okay,
Let me try again.
Try again.
But it may be that the station is not working. We can try the other one.
You've been breaking everything today. You broke the plots earlier. Now you're breaking this.
Yes, I had trouble making some plots, but we can check the other one. Not to give away the answer, but it's going to be 0.00.
You get far more radiation on an international flight.
Right.
Yeah, that's much more. And in the hospital during a CT scan, you get something way bigger.
Colin's got something to show.
Right. So
yeah, you are on the screen.
Yeah, so the average person, I believe, in Switzerland gets about 6 millisieverts of exposure, but 3. Okay, so sorry, it's 3 millisieverts. But they're given these personal dosimeters, and then an operational dosimeter was also mentioned earlier, and I have one here. So the main difference is this one is kind of static. It just tells you cumulatively how much you've experienced in a month, and then you're supposed to read it once a month so they can kind of keep track. But these operational dosimeters can tell you a live rate that you're experiencing. So if you go into somewhere that has a high, has the chance that you get like a burst of radiation, it can alarm you immediately to leave the area. So for example, I have this one because, yep, you can see we get exposed to actually very little radiation.
There you go, 0.00.
Yeah.
Occasionally you might get a 0.01 millisievert.
Yeah, that's a 10 microsievert. That,
very small.
It depends where you are. So for most of the collider facilities, you're going to get exposed to almost nothing. I have this one because I work at the gamma radiation facility, and I don't get exposed to any radiation there either. But because the source is so strong, if something were to go wrong and and someone raised it while I was, or exposed it while I was in the room, this would alarm me to get out.
Also a fun fact that we read it out every day. And we get the statistics almost in live. What people get, what the individual and the group gets, and the radiation protection expert always keeps the eye on and pulls the whistle or blows the whistle, whatever it's called in English. And sorry, it's not my mother tongue. If anything is close to the limits, we are extremely keen on keeping these limits here. So once I made a joke and I regret it, but I don't make any jokes about it anymore. That's a very important thing, that we are subject of the same regulation as the grand public. At least most of us, 99% of people at CERN. And and we are rather keen on keeping these rules.
Yeah, no, we take it very, very
This
seriously.
is one of the basic points that we.
So I know Andres is dying to talk about the upgrade. So I'm going to give a little intro before you do. Sorry,
So
Andres.
indeed, we are
So-
four, and everybody wants to talk. Yeah.
So back to the Large Hadron Collider. So somebody's asking how long it takes to accelerate. So the way that it works is take some protons, we take them from the tank of hydrogen gas, we speed them up a little bit in a previous accelerator, then we push them in to a bigger accelerator and we speed them up a bit more, and then we push them into another bigger accelerator and we speed them up to 450 GeV, so about like half a TeV, and then we put them into the LHC. Once the LHC is full, going from about half a TeV to the 6.8 TeV, where they're almost the speed of the light, that takes about half an hour. And it's a pretty complicated procedure because you're speeding up the protons, and at the same time, you're increasing the strength of the big magnets around the LHC that keep the protons bending around in a circle. Now, Collin was telling you how of those 100 billion protons in a bunch, every time we make those bunches cross over each other, we get what, 60
About
odd
60,
collisions?
yeah.
So and that's like the peak of what the LHC has been able to do. In June, we're going to stop and we're going to go through about 4 years of big upgrades on the detector side as well as the LHC side.
Officially 3.
And things
Sorry.
happen.
Sorry.
And the point of the LHC is what they're going to do is they're adding a whole bunch of extra magnets and special techniques and everything to turn, instead of only 65 protons per bunch crossing, we're going to go for what, like 200.
Yep.
Yeah.
Yep. Yeah. Something like that.
So we're calling this the high luminosity LHC because it's really like, you know, you can think of it kind of like light, where you have like light shining on. We're getting a lot more light, a lot more photons, well, a lot more particles at once colliding. So that's the high. So instead of 65 protons hitting each other every 25 nanoseconds, we're going to have 200 hitting each other every 25 nanosecond. And as a result, our detector has to be upgraded to be able to handle this huge amount of new information as well. I think we lost Andre.
No, he is there, but
I'm here.
he got bored.
Oh, hey.
I have two more tales on this. What you said. If I may, I will tell. If not, then I should.
Okay. So
No,
you
go.
want to talk about the detector upgrades? That was just like
Well, okay. Let me just briefly say something, and then I can move, and then
cool.
Sultan, you can go ahead. So what I wanted to show you is the geometry of the detector that's going to be installed in several years, because we're going to see the progress for that detector in just a minute. So I think you already saw a few photos of our detector, and you saw that it has these inner layers. These are the silicon-based sensors and what we call the tracker. So that's going to be entirely replaced, and you can see some of the new sensors over here. You can imagine if you have a ton of these, you can put them into different geometries. You can make them into barrels, inside of barrels, and then we also have end caps. Now, we are also going to replace what we call the end cap calorimeters. And so these guys, you can imagine if I have the rest of the detector here in the middle, this end cap fits inside of the magnet when we close the detector. So this is like 6 meters in inner diameter. So you can see this guy here. Yeah. So you can see how this will fit inside, but the point is we already have one of these end cap calorimeters. We have to take it out, put it in somebody's garden, and then put the new one in. And so that's what we're gonna show you guys in a minute, but I also want to show you what it's made up 2 types of layers, and the first layer is silicon sensors again. And in fact, I believe HGCal is gonna be the largest. I don't remember. They're gonna set a record for maybe the surface area of silicon sensors. I'm not entirely sure, but it's a lot of silicon sensors, and they look like these hexagons. You can see the silicon sensor here, and then it's sandwiched in between these different layers of electronics and readout. So we're going to show you in a minute the sort of the mechanical support for this that's already taking shape in the assembly hall, which is creatively named because that's where we assembled the detector. So we're on our way there. If you guys want to jump in, feel free.
Sure. Yeah. I mean, the high Lumi LHC is starting what 2029, 2030, but we are already building this stuff right now. That's how big this project is and how long it takes to plan something like this.
Yeah. We got a question. What do you hope to learn from adding and observing more protons?
Ooh.
This is
That's
what
a
I
physics
wanted
question.
to.
Why don't you go for that?
Anyway, go ahead.
Oh yeah, so yeah, that's a good question because basically the way we advances is we can increase the energy to access higher energy or bigger particles, right? Because the more energy we put in, the more mass we can get out. Or we can try and study to extreme precision the things we can already access. And we have more collisions, more protons, and we have more data. Basically, it comes down to statistics. We want as much statistics as possible. So see as many Higgs bosons as we can, and to make the most accurate comparison to our super accurate theory.
But what is very important that not every proton-proton interaction creates a Higgs boson.
Right.
It's a very rare process. I know one number of a simulation for the configuration of the time when we found the Higgs boson back in 2012. And this was something like one Higgs boson in statistics, one Higgs boson in every 3,000 billion proton-proton collisions. So what we are studying are very rare processes.
Right.
And that's why it is super important to increase the proton-proton collision rate, the luminosity.
All this quantum mechanics is probability. So we don't always get the same thing. We get them in certain proportions, depending on how likely they are. And since we're trying to study the most, as Zoltan was saying, the rarest, because those are the most interesting, the rarest processes, the more times we do things, the more number of rare processes we should see.
One more thing. It might happen, the reason why we didn't find new physics is that it is even more rare than what the physics that we know. So this might open again something. At least this is one way.
Yeah.
Right. This precision measurement
Yep,
is
exactly
what we want to do right now, since
Like you might have heard of dark matter and dark energy. So if we take everything that we know about the universe, then that adds up to 5% of the universe. So there's 95% of the universe that we still don't know what on earth it is.
This is a great
yeah, we're trying to figure this out, and maybe so we can create Higgs bosons. It's rare, as they've said, but one of the hopes is that if we create a Higgs boson, which is already very rare, most of the time the Higgs boson doesn't live long, but it transforms into usual stuff like electrons and protons and that sort of thing. But it could be a very, very rare thing that the Higgs boson turns into dark matter. And so one of the things that we could gain out of having more and more and more and more and more collisions is that we can start seeing these super rare things and maybe even start to understand what like more than 5% of our universe is.
So guys, I will jump in just a second just to illustrate the scale very quickly. So we have this banner behind us, and this is to scale. So it's 15 meters, and that's the size or the diameter of our detector. And in fact, we're standing on top of the main shaft. So this is a slab of concrete that I'm standing on. It's like 2 meters thick, I think, something like that. But we can move this slab out of the way, and then it's a hole in the earth that's 97 meters deep. And I just very quickly wanted to show you that this thing is what we call the Circuff frame. And this is something we install that fits just inside of the magnet. It takes we move the end cap calorimeters out of the way, and then we can install these things temporarily. So we have access to what we call the tracker bulkhead area. So this is if we need to access peripherals to the tracking detectors. Okay, so we're gonna go and show you guys the progress for HGCal. You guys can continue with questions or whatever you like.
Oh, there's a question on how long it takes to analyze the data. Well, how long is it taking you?
Yeah, so we're wrapping up, I think, well, it's okay. So the data sits around for a long time and people analyze it for many years afterwards. My personal analysis has taken about 2 years, but it depends on also what you're trying to do. If you're trying to redo some existing analyses, you can maybe get that done within a year. But if you're doing something really, really new and novel, or that can take a while to validate, because you have to check with so many different people. As we said earlier, there's like 6,000 people on the experiment, and there's hundreds of people focused on very small things. So like if you want to use a muon in your analysis, you have to go talk to the people to validate your muon objects and say, this data you put together, that's a muon, we're confident in it. You also do the same thing for electrons and photons and energy. So there's a lot of time spent in these analyses just checking with other people and other experts to make sure you're doing it right. So I would say it takes about.
Yeah, so sorry
go ahead.
to interrupt. We're a little bit short on time, so I wanted to make sure to show HGCal, and then we'll head back to the control room. So this is what the frame, let's say, for HGCal looks like. This is, let's say, the mechanical support. So the detector's not yet in here, but you can see there's some of the cooling infrastructure is already in place. And taken together, when the detector's ready to be installed, this will weigh about 250 tons. So this is an extremely heavy part of the detector. I'm sure this was already mentioned, but our detector taken together is about 14,000 tons. So you can think of that as 14,000 small cars. And so HGCal, you can see that there's some gaps around here. So the actual sensitive detector components will be sort of slid in. We call these cassettes that will go in. And I mentioned that some of them are going to be based on silicon sensors, but they're also in the, let's say, in this region, right, in the more forward region, that's going to be calorimeter, so tile calorimeters. Okay, so I'll leave it there and we'll head back to the control room. Let me know.
This is the first time we show this to the grand public. It is so
I
recent.
only saw it for the first time
Yeah,
today
exactly,
when I
exactly.
waited in the
It
hall.
has never been on the
So
virtual
cool.
visits
It is
before.
so cool.
And
that thing-
those big pockets are mine. I
Oh.
work for the so-called gem detectors in the muon system, and our ME0 detectors
Yeah.
will
Are
go
gonna
in.
slide
Yeah,
in there.
exactly. Yesterday
That's
we tried to slid in
Exactly.
the demonstrator, and we were really happy. It went in without any problem.
But the entire point of this HGCal, the high granularity calorimeter, is to measure the energy of a particle. So that's all it's measuring, not its direction, not its charge, just its energy. Super cool.
Mhm.
What is the most exciting thing that we have found, and what is something that we've learned? Oh, learned so much. Personally, I learn something new every single day. Like today's the first day I see this thing.
I think the biggest triumph of the LHC has been the Higgs boson, right?
The Higgs boson
which
was very cool.
proved the existence of the Higgs field and what gives mass to all particles.
How do you determine what type of particle is a Higgs? So this is okay. This is a good question, because we can never say 100% for sure, but we can get a pretty good idea.
Right. So yeah, a lot of the things that we're detecting indirectly, right? So we can't actually see a Higgs boson. It's neutral, so it doesn't leave a signature in any of our detectors. It also lives for so briefly amount of time that it doesn't travel very far from the interaction point before decaying into other things. So basically, we have to detect all those other things it decays into. Oftentimes, it works down to stuff like electrons or muons or photons. And basically, we follow those things we can see very well, and we work backwards. So
Believed to be.
So on the screen, we're going to put a picture of what we think was a collision that where we produced a Higgs boson. So what's happening here? Okay, so we had the proton smashing. One proton from each beam smooshed together and had enough head-on collision energy to create a Higgs boson for a very,
We
very
believe
small,
it to be a Higgs.
Yeah, for a very, very small fraction of a time. Now that Higgs boson doesn't live for very long, so it decayed, it transformed, and in this case, I think it transformed into 2 muons and 2 electrons. So those red lines there show the muons, you know, shooting off. And the big long green lines show the electrons that have shot off into our detector. And what the physicists did was they went filtering through the data, looking for events where you have 2 muons and 2 electrons. Then you have to check that they come from the same place.
Mhm.
And then you have to add up the mass of all those 4 things. And then you get a number. And if that number is close to the mass of the Higgs boson, then you can say that that's pretty good chance that that was a Higgs boson that turned into these 4 guys.
Actually, this we calculate for each of these events, and this peaks around.
Around
that
125.
statistically peaks. Let me see if
Yeah.
I find something. Go ahead.
So that's kind of how you do it. Yeah, but yeah, discovering the Higgs was very fun.
Yeah.
In a way, it might have been more fun to not discover a Higgs, because like the Higgs was predicted. We didn't know what the mass would be, but we knew that there should be something like it. Okay, it's very fun to know that you're right. I like it, but
But we still have so many questions.
We-
Okay.
still, that leaves us with only knowing 5%. So there's still, even though we found the Higgs, we still only know 5%. Crazy.
Andres has just arrived. I know.
Okay.
Hello. So
yeah,
we
he
wanted
is-
to show
he is
you
here.
some live images. Yeah.
Yeah, exactly. Can you just go around in the control room?
Yes, of course. So we are at the technical shifter station, and we have 24/7. We have always in person a technical shifter and a shift leader, and they are both in charge of safety, both detector safety and human safety, and especially the technical shifter. Since you see the station here, there's monitoring for all sorts of quantities in the detector, and there's also controls. So that means that we can change the high voltage of any of the systems in CMS, and we're monitoring for any problems that could be water leaks, it could be fire alarms, it could be any kind of problem. Yes, and you also saw, I just wanted to make sure you guys see live images from our detector. So this is now, it's right now in the detector. And of course, as we said, the experimental area is closed right now, but we have these live cameras and you can see the images. This one in particular is pretty interesting. You can see the view of this is from top of the detector, but this is the view of the particles going into our detector. Yep, and as I mentioned, we have the shift leader who is in charge of safety and data taking. So we have a different shifter every 8 hours, but we have continuously shifters here. And they're responsible for safety on site, and they are responsible for the data taking. Then we have the data acquisition station, and here the data acquisition shifter will control the data taking and supervise the data taking, monitor everything from the data coming in to its transfer eventually to the long-term storage at CERN. We have the trigger shifter. We talked a little bit, I hope, about the trigger, which is sort of this filtering system, and it also requires monitoring constantly. So we have a dedicated person who is monitoring the data acquisition, the trigger.
Just to interject, Jessica, that answers your question. We don't keep all the
No,
data.
we actually throw out about 99.9% of
Yeah.
it, because we're trying to study the rare processes, right? So if we just keep all the stuff we already know, well, that's not very interesting. We're looking for the rare stuff.
Out from the 40 million, we keep something like 1,000.
Yeah.
Yeah,
per second.
That's the trigger's job. Is
But when
to
we
do
do
that
collect it, we
filtering.
do keep it forever. It's stored here and all across the world in duplicate. And then when we don't need immediate access to it, we write it to tape, and we have huge warehouses of stored data.
Yep. So I didn't want to
not mention DQM. So DQM is the data quality monitoring, and that's also, of course, a big part of what we do. Is we take as much data as we can, but we need to take as best quality data as we can. So that's the short summary. I know we're a bit low on running low on time.
Yeah, I think we got like 1 minute left to wrap it up, but to just flash answer some of the last question, who funds all of this? The member states of CERN fund the accelerators and the infrastructure, and then we have universities and labs across the world who are members of the CMS experiment who actually fund the building and the operation of the experiments themselves. So yeah, all around the world, lots and lots of people. And what fields did we study at school? I did physics, chemistry, mathematics. Those were the most important ones, I think. It's
Yeah,
pretty
physics and
standard.
chemistry for me.
Yeah. And then what is something we've learned from all of, okay, what is something you have each learned from all of this? On the
Too many-
physics
too
side
many
or
to
like
list.
not on the
Yeah,
physics
there's-
side?
I don't know. I don't know how to answer that. I would just say that you develop a passion for this, right? And I think that's you constantly have to learn more. At least from my point of view, it challenges you all the time. When you think you become an expert, there's a lot more you still have to learn, and I really appreciate that. I don't know if it's something I've learned, but it's something I've developed over the years.
I mean, yeah, it's too many things to count or even say.
One of the things I love is like how, you know, you were talking about doing an analysis. So you've done an analysis and now you get more data. So you want to redo the analysis on that bigger data set. And then also with AI, we've been improving. So like we save the data because we could go back in the future and have new techniques that allow us to squeeze more out of that same data set. So, you know, the data that we're getting now is going to keep us busy for a long, long time. So hopefully you guys can come and join us one day over here. I think that we probably need to let you get on to
One more
your
question
next
concerning whether the collider runs constantly or it is stopped from time to time. I think it's quite relevant.
Yeah, that's true.
So it runs as constantly as possible, but pretty much every winter break we stop, and there's a period of maintenance. And
Something like 3 months.
That's usually about 3 months. This year was a bit shorter, or shorter than normal. But yeah, and of course we try to keep the collider running all the time, but it's one of the most, arguably the most complicated machine that humans have built. So it breaks all the time. It requires, and that's of course the LHC, but even CMS, it's so complicated that it requires you know, a whole team of people to constantly just check that everything continues to operate, and then we have to replace all sorts of whatever breaks we have to replace immediately. And so like, yeah, all of us here are very much involved in that.
So thank you, all of you, for your amazing questions. They were really fantastic. I hope you enjoyed the quick little tour. Thank you, Andres, for taking us underground. Thank you, Collin, for sharing your insights as well. And thank you to Noemi and Zoltan behind the scenes. Who was doing the nice camera work and everything.
Thank you all so much for your time. Yeah, we really enjoyed this. I know our students have loved being here.
Excellent. And yeah, really hope that we see some of you here at CERN in the future. There are Arizona University, I think, works on the Atlas experiment. So yeah. Don't go to the competition though, come here to CMS.
Yeah, we need to get Arizona State involved because I think it's the U of A that has a lot of
yes, that's right. Yeah. Awesome.
But we'll make it happen.
All right. Thank you so much for joining us, everyone, and have a lovely rest of your day.
Ciao, ciao.
Bye.